Whoops. All right, let's go ahead and continue with our discussion on gravity. So we are now looking at the gravitational field, and I just wanted to touch on this, noting that gravity is in fact a vector. Okay, so we have that it moves with some sort of um, position vector, or it's based in some r hat here. Okay, so radially. Okay, so in every direction of the radius of whatever the object may be. Okay, and so we get these field lines, and a lot of times when we think of field lines, we'll think of magnetism, but in this case, we also have it with the gravitational field. Okay. So let's now look at gravity away from the surface. So we were looking at equations that were able to describe gravity that is only for a radius greater than or equal to the radius of Earth. Okay. But we can look at the opposite. So we can look at radii that is less than the radius of Earth. Okay. So we can look at this with Gauss's law, or density is equal to mass over velocity, like we did with our previous problem here. Okay. So we get this using Gauss's law. And we did this in our last example. Let's see if I can find it. Not this one, but this one. Okay, so the one about looking at the moon, the value of G on the moon. Okay, so we had to use these ideas of average densities. Okay, so we are looking at the same thing, but now kind of putting it all together. Okay, so now if we use this idea and plug it in, okay, we find that G is equal to 4/3 of uppercase G, or capital G, times rho pi r. Okay, again, where rho is m over v. This is density. Okay. Now, the value of G decreases linearly as you descend into the center of the spherical planet. Okay, we will notice that. Okay, so we need to then find a way to look at the gravitational potential energy beyond Earth. So let's look at this figure here. So we have the Earth here, and say we have some object orbiting at R1 and another object orbiting at R2, okay? And we want to know the potential difference, or gravitational potential energy difference between those 2 points, okay? First, we will need to remember that in the past, our potential energy, difference in potential energy, is equal to negative the integral of the path, so R1 to R2, times, or of f dot dr. Okay, so hopefully you guys remember that from us talking about gravitational potential energy in the past. Okay, so we will put this guy to use. So first we have a radial motion. Okay, so motion in that r direction. Okay, so away from the center of mass. And with that, our F is actually going to be in that same direction, right? So our gravitational attraction is going to be in that same direction, okay? Actually the opposite, but I'm thinking like parallel, okay? So F is going to be in one of these directions, right? If we have some object out here, it's going to be radial, right? Okay. And it may be in the opposite direction, okay? But the fact is, we have this force in the same parallel direction, okay? Now, when we're looking along this arc, okay, so from that R1 point to R2, we'll then have to travel along this arc here, and that motion is perpendicular to our force. Okay, so dr is now perpendicular to that force, because again, force is radial. So in that case, we don't have any work that is done along that path. Okay, so the path that we're really interested in is going to be this guy here, or in the radial direction. Okay, so we have that delta u is going to be equal to negative, again, the integral from R1 to R2 f dot dr. Okay, and remember, I'm going to put this real quick. Our difference is going to be u2 minus u1. Okay, right? So u2 is this second portion here. u1 is that first portion. So this guy is going to be canceled. Okay, so we'll just be left with this one here. So we have a negative times a negative, which is going to be a positive. And our u is going to be our f dot dr. Our f we found earlier is gmm over r squared, right? Okay, and we can pull our constants out of the integral, and that's what is done here. And then they go ahead and integrate and get this expression. Okay, so again, this is delta u is equal to this. And so we can then put this in general terms that u is going to equal negative g m sub e m over r. Okay. Okay. So we can go ahead and put this into use with this first example, example 13.6. How much energy is required to lift the 900 kilogram Soyuz vehicle from Earth's surface to the height of the ISS, which is at 400 kilometers above the surface? Okay, so we have our mass. We have that it started at Earth's surface. So R1 would be equal to 0 meters. And then R2 is going to be the height of the ISS, or 400 kilometers. So 400 times 10 to the third meters. Okay. So what we'll do is say that our travel, our distance here. Okay, so let me go ahead and write this out. So we've got delta u is going to equal u2 minus u1. Okay. Let me see. And then we have this equation here. But we're looking for this one, right? Yeah, so we've got u is equal to g m times m sub e over r. Oh, it's a negative as well. Let me think about this for a second. Is it going to be positive or negative? Is this u1 or u2? u1 give me just a second here. All right, I remember what I was missing. So this is correct. This is what we're going for, but our radii are not correct. So if we are looking at in regards to the surface of Earth, yeah, it would be the radius is 0, but it's not 0, right? Because we have the whole radius of Earth to include. Okay, so we're at this height is equal to R1, but the radius of Earth is actually our radius, R1. Okay, so our radius R1 is going to be that plus the radius of Earth. Okay. So we actually have delta U is equal to negative G M E over, it's going to be this 400 times 10 to the third plus R sub E, where R sub E, should write that down, it's going to equal 6.37 times 10 to the 6 meters. Okay. So the radius down here, I'm going to actually just leave it for now like this for just a moment. And then minus plus GMME over our R sub E. And I'm going to simplify this. So we've got GMME times 1 over 400 times 10 to the third plus RE plus, actually this is a minus here, 1 over RE. Okay, hopefully you guys followed that. So this is me pulling out GMME out of this here. Okay, so then we have 6.67 times 10 to the negative 11th Newton meter squared kilogram squared times our mass, which is 9,000 kilograms, times the mass of Earth, which is 5.95 times 10 to the 24th kilograms, okay, times a negative 1 over, let me do this in my calculator really quick. We have 6.37 times 10 to the 6th plus 400 times 10 to the 3rd. That gives us 6.77 times 10 to the 6th meters, and then plus 1 over 6.37 times 10 to the 6 meters. Okay. So I'm going to do this portion first. So I've got negative 1 over that number. Okay. Plus 1 over 6.37 times 10 to the 6th. Okay. Then multiply that by big G, 6.67 times 10 to the negative 11th times 9,000, whoops, times 5.95 times 10 to the 24th. Okay. So our change in potential energy, gravitational potential energy, is going to be 3.31 times 10 to the 10th. And this is in joules because it is an energy. Okay, so our change in potential energy, this makes sense because we have a positive. Okay, so our potential energy becomes greater as we move further away from the surface, which makes sense. Okay. All right, let's go ahead and move on to conservation of energy. So remember that conservation of energy states that our initial energy should equal our final energy, right? Or the change in energy should equal 0. okay? And remember that energy is equal to our kinetic energy plus our potential energy, okay? And so this is what we have here. Our kinetic energy, or our first kinetic energy, our initial kinetic energy, plus our initial gravitational energy is equal to our final kinetic energy plus our final gravitational potential energy, okay? Now, from this, it was learned that we can solve for an escape velocity, and that is the minimum initial velocity of an object that is required to escape the surface of a planet and never return, okay? So what does this mean? So if we're, like our satellites are up here, right? Orbiting Earth, okay? And we want them to stay in that orbit. We don't want them to fly away. But if we want our little satellite here to fly away and go to another planet, we need it to give it some sort of initial velocity that will give it enough, basically, kinetic energy to get past this pull of our gravity, okay? So how did we figure that out? Well, what we did is we went ahead and used this conservation of energy idea, okay, and said, okay, there must be some initial velocity value, and we're going to call that V escape velocity, okay? Then our R is going to be whatever the radius that we start at. May it be the surface of Earth or whatever, right? So it would just be the radius of Earth. Then at the end, it'll take away all of that kinetic energy. And so we'll have V is equal to 0. So that velocity will go to 0 in the end. Okay. And then one last component is the radius. So if we want that object to never return, aka like go to another planet, okay, maybe orbit over there. So say if we're going to Saturn or Pluto with some kind of satellite, that radius is no longer just orbiting the Earth, right? If this is the Earth, we want that radius to be as large as it can get, okay? So we set that radius equal to infinity, okay? Now, what is 1 over infinity? 1 over infinity is 0, okay? It goes to 0. Whoops. Okay, so now we have this equation of 1/2 mv squared minus gmm over r equals 0. And we can solve for our escape velocity as so, okay? So our escape velocity is now the square root of 2gm over r, okay? All right, so let's go ahead and look at an example. This is 13.7. It states, what is the escape speed for or from the surface of Earth? Assume there's no energy loss from air resistance. Compare this to the escape speed from the sun starting from Earth's orbit. Okay, so I'm going to do the first one. I don't have the data from the sun, so that'll be here in a little bit, but let's start with the first part. So the escape speed from Earth. So V escape, we just found was 2gm over r, correct? Square root it. Okay, so this is going to be 2 times 6.67 times 10 to the negative 11th. You'll probably remember this number by the time we're done with this section. Newton meters squared over kilograms squared times the mass of the Earth, which is 5.95 times 10 to the 24th kilograms. And then we divide that guy by r, or our radius of Earth, which is 6.37 times 10 to the 6 meters. Okay, and square root that whole thing. Now, it does state that we're looking at it from the surface of Earth, meaning our radius here is just going to be the radius of Earth. Okay. So because we're at the Earth's surface. Now, if we're in orbit, it's going to be different, right? Okay. So let's go ahead and put this into your calculator. So we've got 2 times 6.67 times 10 to the negative 11th times 5.95 times 10 to the 24th. Divide that by 6.37 times 10 to the 6th and square root it. All right, so our escape velocity is 1.12 times 10 to the 4th meters per second. Or if we want to put it in something else that we would recognize, let's go ahead and put it into at least kilometers per hour. Okay, so we've got 3,600 seconds in 1 hour. And for 1,000 meters, we have 1 kilometer. Okay, so we'll say times 3,600 divided by 1,000, and it is about 4.02 times 10 to the 4th kilometers per hour. Okay. You can also convert that into miles per hour if you want. I just wanted to kind of look at it in a kilometers per hour perspective. But this is, this is about, let's see, 1, 2, 3, 4. This is 4, 0, 2, 0, 0, right? Kilometers per hour. So that's 40,000 kilometers per hour. So that doesn't seem right. Maybe it is. Let's see, about 11,000 meters per second. Let me double check that. I don't know why, it just kind of seems high right now. Let's see. Yep, okay, it's right. Maybe they will do it for us. Kilometers per second. Okay, well, yeah, so it is correct. I just wanted to make sure because that seemed like a high number, and I guess that would make sense, right? Because we do have gravity that we have to push against and completely get out of the Earth's orbit in order to escape, right? So that makes sense. Okay. So I am going to continue our next video, starting with circular orbits. So we'll see you in the next one.